Okay, we've been talking about geostrophic velocities. Now we're going to talk about how geostrophic velocities make up the gyre circulations. We're going to focus on the pressure gradient force. So we're going to think about where the pressures are coming from, how that works, how that's related to the Ekman transport, and then it's going to give us a basic concept of where the gyres come from. One of the things that's important about gyres are the boundary currents, the western boundary currents, the eastern boundary currents. Those are also associated with pressure gradient force, and so we're going to touch on those as well. You'll know that the reading here is moving ahead into chapter 10, so we've gone through 8 and 9 and now 10, and then column chapter 4 gives us a lot of these great illustrations that we're going to talk about. So, we're going to remind ourselves about the review of balances. We're going to jump onto geostrophic flows resulting from the Ekman convergence and divergence, and then we're going to touch on the shallow water equations at the end. Okay, review of balances. Here's the full momentum equation. We talked about superposition last time. The superposition allows us to individually think of different dominant balances that might be made by a pair or three of these equations three of these terms in this equation at a time. So here's the inertial oscillation contribution, and that comes from having a small advective Rossby number, small Ekman number, but an order 1 temporal Rossby number. The Ekman layer is when we have an order 1 Ekman number, and then we have the other components small. The hydrostatic balance is a vertical gradient of pressure together with the gravity force. The geostrophic balance is the horizontal gradient of pressure together with the Coriolis force, and this is the one that happens these pressures are actually arising because of anomalies in the horizontal of the hydrostatic balance. The Taylor-Proudman theorem puts together the hydrostatic balance and the geostrophic balance, but it doesn't handle horizontal variations in in density. And so if we neglect horizontal variations in density, we get a three-way balance now for the Taylor-Proudman theorem. It says that we get motion in vertical columns. And what we ended on last time was the fact that if we have horizontal variations in density, like piles of bricks next to piles of pillows, then we actually get shear in the vertical. That shear is called the thermal wind shear, and that's the last balance we have to worry about. So the thermal wind is geostrophic in the horizontal, hydrostatic in the vertical, but unlike the Taylor-Proudman theorem, we have no assumption that the density is constant from place to place, as in the constant density version of the geostrophic flow, nor is it simply barotropic geostrophy, that is where the pressure is a function of the density alone. Let me say that backwards. Density is a function of the pressure alone and not of anything else, like location in space or salinity or temperature, just rho of P. Okay. So, what do we see when we go out in the real world? Okay, well, this is not the real world, this is the climate model, but this is a nice version of showing us that this is a map of sea surface temperature, and we're seeing lots of currents, we're seeing lots of eddies, we're seeing lots of big cyclones, we're seeing lots of big anticyclones. You notice that the clock is ticking by in months rather than in hours, so we are safely in the small advective Rossby number limit, and temporal Rossby number limit, where the flows are large scale and slow in time, and the salinity and temperature are moving around, implying variations in the density from place to place. The temperature is being carried around by geostrophic flows. Things are changing with seasons. There's a lot going on. We'd like to understand this. Here's a different way of visualizing it. This is just focusing on the velocity field. Oops, I wanted to start playing. This is just focusing on the velocity field, not on the salinity and temperature. But you can see the velocity is highly variable in time, highly variable in space. You can see there are lots of little cyclones and anticyclones everywhere. There are these big currents at the equator. There are these big western boundary currents that are on the western side. There's not really a big current on the eastern side of each of these subtropical gyres. There's a really big one on the western side of every subtropical gyre. And then the ACC is this chain of high velocity currents that goes all the way around Antarctica down here. Okay. So, Let's swing back to what we talked about last time. Geostrophic explanation of gyres. We have sea surface highs. The sea surface highs drive anticyclones. Sea surface lows. The sea surface lows drive cyclones. The high pressure results from convergences in the Ekman transport, where stuff is being piled up. And there are anticyclones, where we have high pressures. But if you look in where those highs are, the velocity field, which is what's being mapped here, or actually it's the kinetic energy field, but essentially the magnitude of the velocity field is being plotted here. It's not symmetric. It doesn't go like southward, equatorward, as fast as it goes northward in the North Pacific. Same with the North Atlantic. In the South Pacific, it goes fast. It's going the opposite direction, but it's also not traveling equatorward and poleward at the same rate. It's going much, much faster when it is going poleward than when it is going equatorward. Okay. We want to start thinking about why that is. So if you made a schematic of this, you might draw these broad, slow currents, and maybe something like an upwelling current, an eastern boundary current that's in the upwelling zone on the far eastern side, where the offshore Ekman transport is. But the big currents, the Kuroshio, the Gulf Stream, the East Australia Current, are all here on the western side of each of these ocean basins. The Oyashio is the one up here in the North Pacific subpolar gyre. Okay. Interesting. So we're going to start to put together the pieces to understand why it is that those big currents are over on the western side. And we also just want to understand a little better how the pressure field gets there from the Ekman convergences and divergences. And we're going to see a lot of pieces of our story come together there. Okay. So we have the Ekman convergence and divergence story. Why is it stronger in the western side? Western boundary currents. What about eastern boundary currents? Where are they coming from? Are these deep? Where are they shallow? What about the overall gyre budgets of mass and heat? Okay, well, we talked about the signatures of upwelling, and you've now written a paper on those, or are in the practice of you're about to finish writing a paper on those. And those are cold water anomalies in the sea surface temperature, and high chlorophyll anomalies because they're bringing up nutrient-rich water to the surface. They're at the equator, where geostrophy breaks down because we can't divide by F. And also, so too does the Ekman flow, which maybe you've thought about a little. We can talk about that later when we talk about El Nino. But in these coastal upwelling regions, there's something else going on there. And we talked about this casually. Well, not casually. We went through the schematic in a pretty detailed way, where we would have Ekman transport to the right in the northern hemisphere, to the left along the equator, because the trade winds go from east to west. And so that means that there's a pressure field that goes together with this, with low pressure on this side and high pressure on this side. These trade winds basically are piling the water up downwind and sucking it out upwind. So we get a high pressure, low pressure gradient that goes like that. And so there's both a geostrophic component as well as an Ekman component. I'm not going to dwell on that too much for now. But we have these winds going like this. We have this sea surface height anomaly. We have this upwelling anomaly. And so these kinds of features, where we have a divergence in the wind stress, or a divergence in the wind-driven Ekman transport, is going to lead to these sea surface highs and lows. What about in a coastal region? Well, in the coastal region, if we have an alongshore wind that's blowing an offshore Ekman transport, we expect there to be upwelling. We expect there to be a sea surface low here as we're pushing this water away. We expect it to be made of very dense water, so maybe there is a greater accumulation of mass with depth, a weight with depth here than there is over here offshore, which leads to baroclinicity in the problem. How does that all work out? Well, if we think about a schematic of the picnic line and this upwelling flow going this way and going this way, we have a low pressure, high pressure, low pressure, high pressure situation, just like we saw in the thermal wind case. So hey, this sloping isopycnal surface that's cutting across isobars, which are relatively horizontal here, is actually a perfect example of a thermal wind relationship. So if we go through our game where we have the Coriolis force balancing the pressure force from high pressure to low pressure and the opposite below, we'd expect there to be a flow out of the board in the northern hemisphere and into the board like this. And that's in fact what happens in the California current. There is an offshore flow like this, a southward surface current called the California current, and then there is a California undercurrent, which is actually a northward current at deeper depths. Depending on the location of the wind forcing and like the slope of the topography, you can get much more complicated patterns with all kinds of weird, funny other circulations. Not too hard to figure out, but our thermal wind relation here is definitely in play at eastern boundary currents in an upwelling zone. And remember, our thermal wind game is that we've got bricks next to pillows. Our buoyancy gradient, or our density gradient, going the opposite direction, is pretty uniform with depth in this case, but the pressure gradient definitely is not. The pressure gradient goes from high to low, from left to right at the top, and from high to low, from right to left at the bottom. And that leads to this baroclinicity, and then that leads to a thermal wind relation, which means that there's shear, vertical shear, in the geostrophic velocity that's governed by the horizontal buoyancy gradient. Okay, but what about the pressure in the gyres? That was the eastern boundary upwelling systems. That's only a little tiny part of this larger gyre flow. What about these large-scale winds? What are they doing? Not the longshore winds near the continents, but these big ones out in the middle of the ocean. Well, last time we said that the zonal winds go like this is a pretty simple understanding of how they flow. Westerlies about in the roaring 40s, trade winds, easterlies at the equator. And then we said, hey, look, the Ekman transport that comes from those goes like this, to the right of the wind in the northern hemisphere, to the left of the wind in the southern hemisphere, which implies that there's a convergence at all the C is here, and a divergence at all the D is here. And now we're starting to get sophisticated enough to recognize that when you have a diverging flow, you tend to have a sea surface low. When you have a converging flow, you tend to have a sea surface high. Just like we saw in the plug hole experiment, you had a sea surface low where the flow was coming in and being sucked out the bottom. When we converge and we don't have a plug hole in the bottom, we actually pile up a little bit. We're going to get a little more sophisticated than that. My advisor, Joe Podlosky, always told me that this was a lie. This does not tell you what happens in the pressure field. That is true. It is a useful way of remembering it, but there is a more subtle balance going on with something called vorticity that we're going to talk about in the future weeks that helps realize why this convergence actually leads to kind of a stopping up, a backup, and a sea surface high. Okay, but now we have a new wrinkle. We don't just know where the convergences and divergences are. We know where the highs and lows are, and then we actually know one more step. We know where the cyclones and anticyclones are. So around every low pressure anomaly, here, here, and here, all the way around the ACC, we have a cyclone. And in the northern hemisphere, a cyclone is counterclockwise. So the subpolar gyres go counterclockwise. Around every high, we have an anticyclone, which is in the northern hemisphere, a clockwise circulation like this. And hey, look, if the Gulf Stream is this part, and then the rest of the gyre is that part, that's the right direction. If the Kuroshio is this part, and then the rest of the North Pacific subtropical gyre is this part, goes in the right direction. If the Oyashio is this way, we get something in the right direction. And if the Labrador current and Erminger current go this way, we actually are going the right way in the subpolar North Atlantic as well. What about the ACC? Is that a cyclone or an anticyclone? It's just going from west to east. Well, if it's a low pressure anomaly that goes all the way around, and low pressure, so cyclone is like this in the southern hemisphere, pointing up like this, that is actually a low going all the way around, around, and around. It is going like a cyclone. It's going in the same direction as the rotation of the Earth. It just doesn't close within a basin. It just loops all the way around and around and around Antarctica as it goes. These pressure anomalies that we showed from the model is in fact very consistent with this kind of low, low, high, 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 low, low. Let's see. Low, low, high, 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 low, low, low setup. And the velocities that go along with this are sitting right on these big pressure gradients. Wherever there's a large pressure gradient, there is a large velocity. It's not true with the equator. We're going to come back to what's going on in the equator. We hinted at it a little bit before in the Ekman divergence of the equator and the pressure gradients that are set up there. We'll talk a little bit more when we touch on El Nino later. But these high pressure places are where the sea surface height is driving a geostrophic flow that's an anticyclone in the subtropical gyres, and a cyclone in the subpolar gyres, and a cyclone, a big old cyclone that goes around and around the Antarctica that's the Antarctic Circumpolar Current. And so the large currents are all explained by parts of these gyre circulations or this ACC. Okay, let's think about it from the pressure gradient force looking from the side. All right, we've got a sea surface high. It happens at the convergence of the Ekman transports. We've got a picnic line depression underneath. How does this work? Okay, the pressure is the weight above you per unit area. So that's the integral from the surface down to whatever depth you're at. The horizontal pressure gradient is the horizontal gradient of this vertical integral. That doesn't care about this z part, but it does certainly care about if there are any horizontal pressure gradients, horizontal gradients in the sea surface height. This is the part we were talking about. This drives the barotropic flow. This drives the constant density flow. Here's the other part of this story. This is the deviation in density. And there should be a horizontal gradient sitting in front of this term. There is, if the density deviates, then you could have a baroclinic response. Geostrophy has this horizontal pressure gradient in it, which has got a horizontal density gradient part in it, but it's also got a horizontal sea surface height part in it, and am I doing something wrong there? Oh, no, I'm not doing something wrong. Yeah, I'm still doing something wrong. I'm still missing a horizontal pressure gradient. Sorry, on these last two terms. Okay, anyway. Sorry. This is the part that's the constant density part. This is the part that's the variation in density part, but it's incorrect because there should be a horizontal density gradient, a horizontal gradient in front of it. Okay, but if we ignore the density variations for a moment, we just get this, where the geostrophic velocity is related to the sea surface height variations. So what's our sea surface height variation? It's high in the middle, low on the sides in the subtropics, which means that we get a flow going around and around and around like this. The Coriolis force is pointing that way, and the Coriolis force has to point inwards because the pressure gradient force is pointing outwards, which means that the flow has to go around and around like this. And so, the two components of the geostrophic velocity, the U component, the zonal component, and the V component, the meridional component, go with the meridional and zonal components of the gradient of the sea surface height, like this, which you can actually integrate from a point on the eastern side to any point on the west you like. So I'm taking this equation and I'm going to integrate from east to west, and I'm going to find what the geostrophic velocity is in the north-south direction. Hey, look, it just depends on the sea surface height variation from the eastern point to the western point. So you get a northward flow wherever the point to your east is higher than the point to your west. So there's a northward flow from this peak down to this low. That's like the Gulf Stream or the Kuroshio. On the other hand, if I go over here where the eastern point sea surface height is lower than the western point, then I get a southward flow. So I'm getting a southward flow all the way on this slope. I'm getting a northward flow all the way on this slope, and this is the rate at which it goes if we're ignoring the density variations. If we integrate down to a constant depth, so all the way above where this picnic line and interesting picnic line stuff happens, but go down a little while, we can actually convert this into a transport. So it's not just a velocity integrated in the x direction, it's a velocity integrated in the x and the z direction. So through this cross-sectional area, we are seeing northward and southward flow that goes like this. So this immediately tells us that if the flow going southward, the transport integrated through that whole horizontal interface balances the transport going northward, the sea surface height on the eastern side of the ocean will equal the sea surface side on the western side of the ocean. So drawing this to this at the same height is telling us that this geostrophic transport is balancing out. If you wanted to have net northward transport, you could do it by having the eastern side be a little higher than the western side. The eastern side be a little higher than the western side. If you wanted to do it, if you wanted to have a net southward transport, you could have the western side be a little bit higher than the eastern side. Yes. I think I said that right. Anyway. So you can start thinking about questions for yourself about this. So how does the sea surface height on the eastern side of the ocean compare to the western side? That's a key question. How does the surface height in the middle of the ocean, where it is highest, relate to the flow to the east and west? How big is the geostrophic transport when compared to the Ekman transport? How does that work out? This one, in particular, how does the surface height in the middle of the ocean, where to its east and to its west, if it goes from an easternmost up to the high and then back down, how much transport is there on this side of the hill versus that side of the hill? Do they have to balance? What controls whether they balance? If this side is compressed over here, but it still has the same vertical change, but just over a shorter distance than this longer slope to the eastern side, is it still the same amount of transport? And how does that work? And it is useful to think this through with the geostrophic transport versus the Ekman transport. Plugging in the numbers, you get about 100 sparedrops of geostrophic transport, thinking on this scaling, and you get about 10 sparedrops for a westerly wind of a typical scale, 0.1 newtons per meter squared. This ratio varies from place to place. So one of the things to examine as we get into these gyre dynamics is the balance between the geostrophic transport and the Ekman transport, and who's bigger and how that all works out. The funny thing about this is that we've been arguing that this convergence, the sea surface high, is there because of the Ekman transport. The Ekman transport is piling up the water, but then it drives a much larger circulation around and around it. This geostrophic transport is an order of magnitude larger. And why is it only a 1 meter sea surface height anomaly at the middle of the gyre instead of a 10 meter sea surface height anomaly? These kind of quantitative questions, rather than the hand-wavy heuristic, are exactly the point that I was saying. My advisor told me all this was a lie, because we can't answer these kind of quantitative questions from the heuristic argument we've made so far. We'll need to turn to vorticity, this other concept, to answer these quantitative questions. But from the perspective of the balances we actually have a nice, we can convert our wind stress into a transport as a function of xe and x west, the same way that we did before. So we have the north-south wind transport, and it's already integrated in z, but now we integrate in the east-west direction to give us a transport through this interface. This is just the game you've been playing in paper number 2. And assuming the wind stress is constant across the basin, we can integrate that integral simply to have an xe minus xw, really similar to what happens with the geostrophic transport through that interface, where we now have a sea surface height evaluated xe versus a sea surface height evaluated x west, with another correction factor, which is the depth of the moving part of this flow with G's over F's and G's over, and rho naughts and F's over down here. Cool. We're starting to get there. The thermal wind is at play here as well, because at the bottom, when the picnic line is depressed, we're actually getting horizontal density gradients as well. And even below that, there's another circulation, which we're going to talk about later, called the abyssal circulation, which goes off in kind of the opposite direction of the surface circulation. It doesn't have to do with wind stresses, it has to do with a different kind of forcing based on vertical mixing that we really need vorticity to understand. And this is going to take us into the transport by eddies as well, which is now we're actually into this century's oceanography when we start thinking about these kind of issues. Okay, the last thing we wanted to talk about was the shallow water system. So the shallow water system is a simplification of the equations of fluid motion, where we just have a layer of fluid of the same density. We might actually stack a few of these on top of each other, but this makes our life much simpler, because now we're just talking about 2D flow in a layer of constant density. You can already guess why I'm specifying this constant density. It's because of the Taylor-Proudman theorem. So within that layer, the velocity is going to be constant in the vertical. Cool. That's going to make our life much easier. So it's going to be a 2D flow in a layer that can have a variable sea surface height, a variable bottom, but it's going to have an anomaly in sea surface height. It's going to have an average layer depth, big H, a varying layer depth, little h, and then there could be bottom topography, which is interesting. Okay, if we go through the process of deriving this, which I'm not going to do for you, but you can go check out in Valis if you want to see how it's done, we get something that is a material derivative for U. So here's our advective and temporal Rossby number sitting here. There's a Coriolis force, which looks like F cross U, just like we'd expect. And instead of the pressure gradient force with the density and everything, we just see this sea surface height one. So here is the essence of those pieces where we have a Coriolis force driven by the sea surface height with potentially large Rossby number in this case. We get those three terms together. Because this is stretching and squeezing like this, we actually have to keep account of that. And so there's a new equation that comes from our incompressibility, the three-dimensional divergence of velocity being zero, or the mass conservation in this case becomes an equation for thickness conservation, that following the motion, the thickness is conserved, except for where the horizontal velocities converge and pile stuff up. And the nice thing about the shallow water equations is that, well, they're easier to work with. And here's just a more explicit representation of the parts of those equations. The shallow water equations also have geostrophy in them because they have pressure gradient forces that have to do with the deviation of sea surface highs, sea surface lows. They have the Coriolis force, so when you have a sea surface low, you get an anticyclone, or sorry, a cyclone. When you have a high, you get an anticyclone. Same kind of flow parameters happen in these simpler systems. When you have multiple layers of shallow water equations, it's the tilt of that interface that plays the role of the horizontal gradients in density, horizontal gradients in buoyancy. So when those interfaces are tilted, you can get baroclinicity, which then gives you something that looks like a thermal wind relation, which looks like this, where the velocity in one layer compared to the next layer has to do with the horizontal gradient in tilt in between those layers. So you can stack them up like crazy. You can make it go like this, and a lot of ocean models, so-called isopycnic ocean models, are built this way, stacked shallow water layers. But the main reason that it's interesting for us to use is because there's a special thing called the reduced gravity case, where we can do a shallow water layer on top of a second shallow water layer that goes all the way to the bottom. And if we take there to be no motion in this deeper layer, we can simplify the equations of motion. Turns out that no motion in the deeper layer means that there's a simple relation in the upper layer, and the upper layer looks just like the shallow water equations do normally, except with a little correction to the force of gravity. And so if we want to use that shallow water equation for the surface layer, we can do it so long as the lower layer isn't moving, which we have been saying over and over again. The pressure field tells us that that's not a crazy approximation. Okay, so here's the reduced gravity system. So the pressure in one moving upper layer over a motionless lower layer, which it's motionless because it has no horizontal pressure gradient, so the horizontal pressure gradients in the lower layer is 0. So here's the upper layer equation. Here's the lower layer equation, which is complicated because it depends on both interfaces, the surface and the interface between. But if we set this to 0, then we can simplify this relationship between those two surfaces and cancel out this one in favor of that one. And it turns out that we get this reduced gravity system, which I'm sure you won't remember because this is the first time you've seen the reduced gravity system, but this looks just like the thickness equation did for the upper layer, for a single layer case, no difference. This is the upper layer momentum equation, and it looks just like the upper layer momentum equation, except one difference. This is only the upper layer thickness, not the total depth. And this G has a prime on it, which means that it's the reduced gravity. It's not the total gravitational acceleration, but it's the gravitational acceleration reduced by the difference between the second layer density and the first layer density divided by the first layer density. So it's reduced. It's not the total density that's moving around here. It's just the difference between the upper layer and the lower layer that drives motion. So we use this because this system is a beautiful one for our pillows. And so now we're just describing motion in the pillow layer. We've forgotten about motion in the brick layer. The brick layer we're assuming has motionless, but the pillow layer is motionful. And here's an equation that describes just the pillow layer. And the G prime is basically the density difference between bricks minus pillows over pillows. So, and this set of equations is really simple. And look, it depends on sea surface height here. So it's the gradients in the thickness of that upper layer. It gets thick when the sea surface height goes up, and it gets thin when the sea surface height goes down. That's all it does. So those two really do co-vary the way we've been describing all along in opposite directions. And as they vary in thickness, this guy is setting up the pressure gradients that go along with that, which is driving both geostrophic motion but also conceivably other motions. And these are really similar to a flat bottom single shallow water layer. So here we go. There's not really any pressure gradients below. So this reduced gravity system is going to be a pretty decent way of thinking about the gyres outside, except for maybe during the ACC. I don't know what I was talking about. Those are just some other examples of geostrophic flow. All right. That's it for geostrophic gyres for now. We're going to come back to this topic with a more powerful tool of vorticity soon.